So the integrand is that the absolute value of t f, all right, and from minus infinity to infinity. Okay, so this is the set of all real valued integrable functions on R. Okay. Now we consider a famous function ft equal to t. So it's just so this function is the so-called identity function. Okay. You map t to t. So this is very common. Then we have that we check the integrability. So this is okay, and by the symmetry, this is 2 times the integral from 0 to infinity, and t dt here. Okay. All right, and this is 2 times 2 to the t square from 0 to infinity, okay? And what is that? This is infinity. Okay, so the integral, this integral is infinity. So which is not finite. So this means that ft equal to t is not in our L1R. Okay? So such a common, a very common function is not in L1R. You can see that. On the other hand, consider exponential function. And the exponent is the absolute value of t. So you can see this function. It's like this one. It's an even function. Okay. So this is our f of t. Okay, you can see that. So it decay exponentially. You can see that. Decay very fast, right? Okay, and so we check it's integral. And as we know, exponential function always non-negative, all right? So the absolute value can be removed. And by the even symmetry, we know this is 2 from 0 to infinity e minus t dt here. Okay, and by anti-derivative, we know this is e minus t infinity and 0 here. Oh, minus, I'm sorry, I forgot to put a minus here. So this is the antiderivative of the integrand, is this one. Okay, and so this is 2 times 1, so this is 2. And which is finite. So that ft is equal to e to the minus t absolute value is in our L1R. Okay, L1R. Okay, so you just check that this set does not include, okay, does not contain some famous functions like this one. Actually, any polynomial function of t cannot be in here. Okay, polynomial function cannot be in here. Can't. We can show that. Okay, but exponential function okay here. Exponential function okay here. How about sinusoidal function? No, because sinusoidal function is periodic, right? So they will repeat. So when you take the absolute value and do the integration, you find that the value is infinite. So the sinusoidal function, sine function, cosine function cannot be here. Can't. Okay? Can't. But exponential function, okay. All right, now we define for L1R, okay, for L1R, we define two algebraic operations. All right, so we define two algebraic operations. One is vector addition. All right, so L1R cross L1R to L1R. So you have to make sure that the addition of two functions in L1R is a function in L1R. Otherwise, it's not well defined. So you have to check the definition is well defined. So this is ft of t. G of t here goes to G of t. Okay? Yes. And the second is the scalar multiplication. So it's R, Cartesian product with L1R goes to L1R. And this is alpha f of t goes to alpha f of t. Right? So it's quite natural. But we have two questions to ask. Ft is in L1R, Gt is in L1R. That's so the question, the first question. The question is that is Ft plus Gt is in L1R if both Ft, Gt is in L1R. So you have the question, you have to ask, to answer. Okay? You have to answer. So now, since we check, so we have to find that to find that this integral is finite. If it's infinite, then the sum is not in L1R by definition. Okay. But this is by triangular inequality. The absolute value of sum of two real numbers is less than or equal to the sum of their absolute values. This is so-called triangular inequality. Okay? And by linearity of the integral, right, you can have here. But because Ft and Gt are in L1R, so by definition, this is finite, this is finite. So the sum of two finite numbers is finite too. Okay? So the answer is yes. All right, so this is well defined. The other question, same. It's alpha f of t in L1R if f t is in L1R. All right, so we have the question. All right, so again, we check alpha f of t, right? We check this integral. But this integral is alpha is scalar dt here. But this is finite, and this is a positive real number. So of course it's finite. So the answer is also yes. Okay, so it's also yes. All right, so now from the answers of the above two questions, now we can conclude that the two algebraic operations are well defined. Okay, so now, so they are well defined. Okay, so they are well defined. And because they are functions, so we can check, because we have experience in doing the sum of two functions, doing the multiplication of a function by a scalar, right? So we have that experience. So by checking the fulfillment of the 7 axioms for a vector space. Okay, we find that they are because the addition of functions is associative. We already know that they are commutative, and we have zero element in L1R, which is just a zero function. Okay, the value is 0 at all the points. Okay, so L1R is a vector space over R. Okay, so there are some vector spaces that we have studied before, like in calculus, right? Okay. Now we may reconsider some spaces. So in our previous studies in this course, let A be an M times N matrix over R. Okay, and the kernel of A, right, KER of A, is a vector space, right, over R, together with the following two algebraic operations. All right, so first one is vector addition. All right, kernel A goes to kernel A. Right, so we have X, a vector in kernel A, and another vector Y in kernel A will goes to X plus 1. Okay, the sum, just ordinary sum of vectors. And the second is the scalar multiplication. So it's R, Cartesian product with kernel A, mapped to kernel A. So alpha x goes to alpha x. Now, once again, we have to check that. We have the question that x plus y in kernel A if both x, y in kernel A. Right? So we have to ask this question. Okay? All right, and so we, right? So now since x, y in kernel A, so we have that ax equal to 0 and ay equal to 0. So that A multiplied with the sum of x and y, okay? Multiplied with the sum of x and y. And by the linearity of metric multiplication, we know that this is equal to A, y. And this is 0 plus 0, so this is 0. So this implies that x plus y is in the kernel of A. Okay? And the answer is yes. Okay? The answer is yes. Okay? So the sum is in kernel A. Okay? Another question here. Is alpha x in kernel A if x is in the kernel of A? Okay. All right. So so since ax equal to 0, so A multiplied with ax alpha x, which is alpha ax, and so this is alpha 0, so this is 0. And the answer is yes too. Okay. So so the definition here, they are well defined. Okay. Right. So so on the kernel of A, we do vector addition as ordinary vector addition in Rn, and we do scalar multiplication as the scalar multiplication in Rn, and we find that they are well defined. Okay, the sum of two vectors in the kernel of A is still in the kernel of A, and the scale vector and the scale the vector in the x is in kernel A, and the scale vector is also in the kernel of A. So they are. And from that, so once they are, All right, so so both questions are about the closure property of the defined and the scale multiplication. So that these two questions is to check the closure property, right? To verify that the vector addition has closure property, right? And scale multiplication also has closure property. Okay. All right, now, since A0 is 0, so 0 is in kernel of A, right? So kernel of A has the 0 vector in the n-dimensional, in the n-dimensional Euclidean space. Okay. And since kernel of A is a subset of Rn, and Rn is a vector space over R. Okay, so Rn, this vector space, they are vector addition, scalar multiplication will satisfy the 7 axioms, of course. And actually, I have asked you to read section 2.1. So in section 2.1, it lists that that the 7 axioms are satisfied. Okay, in Rn. So the kernel of A can inherit the 7 axioms from Rn. So it is a vector space over R. Of course, it's very important to know at first that the 0 vector of Rn is in the kernel of A. Okay? If the 0 vector of Rn is not in the kernel of A, then you have to find another vector in kernel of A, which is not 0 vector, to serve as 0 element, right? And but we are very fortunate that the 0 vector in Rn is in kernel of A. Okay, so kernel of A will inherit axiom number 3, okay, from Rn. Okay, and actually, the kernel of A can inherit all the 7 actions. Okay, and so that the kernel of A itself is a vector space over R. Okay, so do you have any questions about these examples? Okay, so if no questions, then now we have a generic vector spaces. We can consider arbitrary vector spaces, not necessarily Euclidean n-dimensional vector space. Okay, so now we let X be a subset of a vector space V. Okay. All right, and this subset may be finite or infinite. Okay. All right, so the set X may be a finite set or an infinite set. Okay, and a linear combination a linear combination of vectors in A and S, okay, in the set X, is a vector, okay, alpha 1, U1 plus alpha 2, U2 plus plus alpha, and UN, okay, for some vectors U1, U2, up to UN in S and scalars alpha 1, alpha 2, up to alpha n. Okay? So to have a linear combination of vectors in S, X may be an infinite set. You just take a finite number of vectors, U1, U2, up to UN in S, right? Take them, finite number of them, and make this combination, right? All right, so you just pick up scalars and scalars arbitrarily, and then form this one. So you use the scalar multiplication, right? And we know the scalar multiplication give you a vector, right? In V again, right? Because U1, U2 up to UN, they are vectors in S. Or of course, they are in the vector space V. So this is the result of scalar multiplication. Okay, so this is also a vector in V. The second one is also a vector in V, etc., up to the last one. The last term is also a vector in V because the closure property of the scalar multiplication. And then we use the vector addition, right? So the result, the sum here, and by the associativity, you can do the sum of the first term, and then do the sum with the third term, etc. So we can do the vector addition, okay, repeatedly, right? And so by the closure property of vector addition, that the result, this linear combination, is also a vector, okay, in V, right? So we know we are sure that this one is a vector in V, and such a formation is called a linear combination of vectors in X. Okay? Of course, the linear combination may be out of S, right? Even though the U1, U2, and the UN are vectors taken from the S. But when you do the linear combination like this one, the resulted vector is in V, but not necessarily in S, okay? Not necessarily in X. So it's kind of expansion, right? By using linear combination, you expand the set X into a bigger and bigger subset in V. Okay. So when we collect, so we call And so we call the span of S denoted, right? The span of S denoted as SPAN of S is the set of all linear combination right? So it's a set of all linear combinations of vectors in S. Okay, so you can construct many linear combinations of vectors in S, right? And you collect all of them together to form a new set. So this new set is called the span of S. Okay, so of course, we know after this expansion, the original set becomes to a subset of the span of S, of course, right? But the span of S is much bigger. Okay, even though the S is a finite set, the span of X becomes to an infinite set. Why? Because you have infinite many number of scalars, okay, to use to form the linear combinations. Okay, now not only this become to a bigger set, but because we can have the following theorem that is very useful, right? So let X be a subset of a vector space V, then the span of S right? The span of S is also a vector space, right? So it's also a vector space with the same vector addition and the scalar multiplication in V. Okay. So the construction, all right, the span of S comes to a vector space itself with the same vector addition and scalar multiplication in V. All right, so this theorem is very useful. All right, so we let U, V be vector in span of S. Okay. So they are U1, U2 up to UM, and the V1, V2 up to VK in S, and the scalars alpha 1, alpha 2, alpha M, beta 1, beta 2, beta K, such that U is a linear combination, because UV in span of X means that U and V are linear combinations of vectors in S. So U is alpha 1 U1 plus alpha 2 U2 plus plus alpha N alpha m and um. And the v is equal to beta 1 v1 plus beta 2 v2 plus plus beta k and the vk. All right. Now since u plus v, so we use the same vector addition in v. All right. So u plus v becomes 2 alpha 1 u1 plus alpha 2 u2 plus plus alpha m plus beta 1 v1 plus beta 2 v2 plus plus beta k vk. All right. So this one u is so u plus v is also a linear combination of vectors in S. Right, and then in the span of S. Okay? Okay, so this shows that the addition of a vector, the vector addition with respect to from the addition of u v goes to, right? So that the vector addition is a mapping from the span, the Cartesian product of the span of X with itself to the span of S. Okay, so if you take two linear combinations of vectors in X, the sum becomes to a linear combination of vectors in X. So that so the vector addition is a mapping from this Cartesian product to this one. Now, furthermore, for any scalar, since alpha u, alpha 1 u1 plus alpha 2 u2 plus alpha m um is equal to alpha alpha 1 u1 plus alpha 2 u2 plus plus alpha m okay. The alpha u, okay, is also a linear combination of vectors in S, and then in the span of S. All right, so this also shows that the scalar multiplication for alpha and u goes to alpha u is a mapping from R Cartesian product with the span of X to span of S. Okay. All right. So we show the closure properties of vector additions and scalar multiplications on the span of S. So they are closed. They are closed. Okay. Okay. So I will take a break. All right. Now, after the break, I'll show that the span of X has the 7 axioms for a vector space. Okay. Okay. So let's take a break now. Okay. So we have shown so we have shown that the vector addition plus and scalar multiplication in V, okay, are well defined. Vector addition and the scalar multiplication in span of S. Okay. Okay. Axioms 1, axioms 1, 2, 5, 6, 7 can be directly inherited from V. Okay, so that you can check. So these 5 axioms can be directly inherited from the mother vector space V. Now, also, so we have to check axiom 3 and axiom 4. Since we know zero vector is the zero scalar multiplied with U for any U in the subset S by theorem 2.4.4, right? We proved that on Wednesday. That if you select an arbitrary vector and you use the scalar 0, this is scalar multiplication, give you a 0 vector. Okay, so 0 vector can be produced in this way. But this is a linear combination of vectors in X, right? Because U is from S and 0 is a scalar. So the 0 vector in V is a linear combination of vector in S. Okay, and then in the span of S. Okay, so the 0 vectors 0 in V is also in the span of X. Thus, axiom 3 is fulfilled. Okay. Finally, the additive inverse minus 1 times U, okay, of any vector U in the span of S is clearly in the span of S. You may ask me why. Well, when U is in the span of X, we know it's a linear combination of vectors. So that this is okay. So if U is in span of S, of course, it is a linear combination of vectors in S. So, the additive inverse, okay, of U in S also must be, and implies must be in the V. Okay, so any vector in the span of X must be in V, right? So the inverse here, we know that this becomes 2 minus alpha 1 U1 plus minus alpha 2 U2 plus minus alpha m Um. So you can see the additive inverse is also a linear combination of vectors in S. Okay. So it's in span of S, right? And then axiom 4 is 4-field. Okay. All right, so we conclude that. So we conclude that the span of S is a vector space. Okay? Together with the same vector addition and scalar multiplication in V. Okay, so this is the end of the proof. Okay, so basically, the span of X, from this definition, the concept of a span of a subset in n-dimensional Euclidean space now extend to arbitrary vector space now. Okay, and we show that starting with arbitrary subset of a vector space V, the span of X is also a vector space. Okay, with the same vector addition and scalar multiplication in V. We know that. Okay. So now we will summarize a situation in here that span X is a subset of the vector space V, but we show that this is indeed itself is a subspace We also know from this example to know that the kernel of A is a subset of Rn, but we show that the kernel of A itself is also a vector space. Okay. Now this situation can be described in the following way. Let V be a vector space. Okay? Now a subset W of V is called a subspace of V. Okay? If W itself is a vector space. Okay? W itself is a vector space together with the vector addition and scalar multiplication in V. Okay. So examples like K kernel of A is a subspace of Rn. If the matrix A is M times N, so the kernel of A is a subspace of Rn. Another example is that the span of S, okay, is a subspace of a vector space V for any subset S of V. Okay. Okay. This is about subspaces. Now we talk about a lot on linear dependence and linear independence for vectors in n-dimensional Euclidean space. So we will extend the notion to general vector space. Now consider an index set of vectors. Okay, U1, U2 up to UN in a vector space V. Okay, so an index set of vectors. All right, you can see that this list is a finite set. We consider here. Now this index set of vectors in a vector space V is linearly independent, linearly dependent. Okay, linearly dependent. Okay, if there exists, all right, if there exists a non-trivial linear relation right, C1 U1 plus C2 U2 plus plus Cn Un equal to 0 for some scalars C1, C2 up to Cn, not all zeros. Okay, so if we can find non-trivial linear relations here. Non-trivial linear relation means an equation like this one, and the coefficients not all zero. Because if the coefficients are all zeros, then this equation must satisfy definitely. So that's nothing so surprised. It's called trivial. But when we call non-trivial, it's because we can find such a linear relation with coefficient not all zero. Okay. All right. So this is about linear dependence. The index say I forgot to put X here. So my lecture notes, I forgot to put. Okay. So I forgot to put. Okay. All right. So, you please insert X equal. And the index say S is linearly independent. If no such non-trivial linear relation, no such non-trivial linear relations exist. Okay. Okay. So from the definition, if you want to justify an index say to be linearly independent, then you have to show that for any linear relation, the coefficient should be zeros. Means that you can't find any non-trivial linear relation. Okay. Then, so this approach has been taken so many times in our previous discussion. Okay, so this is about linear dependence and the linear independence on for index set. But quite often we will consider linear dependence and the linear independence for non-index set, means that just ordinary set. So a finite or infinite set subset S of a vector space V is linearly dependent if there exists a non-trivial linear relation, a non-trivial C1 U1 plus C2 U2 plus Cn Un equal to 0, okay, for some distinct vectors U1, U2, Un in S, and scalars alpha 1, alpha 2, alpha n, not all zeros. You can, all right, let me finish that. Okay, and the set is linearly independent. If no such non-trivial linear relations exist. Okay, so so look at the difference here. As we know, in an index set, it's possible that the two elements here are equal. Okay, two elements are equals. But for ordinary set, all elements in S should be different, right? They are distinct to each other. Okay, so when we establish linear relation, when we establish it for non-index set, means for ordinary set, the vectors you select must be distinct. You cannot say, okay, U1 select and U2 the same as U1 to form. Why? Because if U1 and U2 are the same, then it's very easy to establish a non-trivial linear relation, right? Because you can just pick up U minus U, right? It's always 0. So U1 is U, U2 is U. And then you establish such, which is non-trivial. But it's not allowed, right? So it's too cheap to say that. Okay, so for ordinary set, the vector you select must be distinct vector. This is a requirement. But for index set, because the index, the vector has been indexed, so that the position has been set there, so that we allow them, some of them, to be equal to each other. Okay, so that's fine. As we deal with columns of a matrix or rows of a matrix, because columns of matrix may have the same columns, right? Okay. Okay, so so you should be careful here, right? You have to, when we talk about linear dependency, you will to see if whether the set we consider is indexed or not indexed. Okay, if it's not indexed, then be careful. If when you form linear relation, the vector should be selected as distinct vector from the distinct vectors there. Okay, otherwise the concept almost the same. Okay, the concept almost the same. And for index set, we usually consider finite index set. But for ordinary set, the set can be infinite set. So even though X is infinite, the X has many infinite vectors. But if you can select a finite of them, for example, 2 of them, only 2 of them, right? Such that you can find a non-trivial linear relation, then the whole set is linearly dependent. Okay, so that even X is infinite, a linear relation should be selected from just finite number of distinct elements, distinct vectors. Okay, all right. So this is about dependence. All right, so let's take an example. Suppose x 1, 0, 0, 1, 1 minus 1. Okay. Right. So this one is linearly, right? This set is non-indexed. All right, it's a linearly dependent subset of R2. The reason is that we can find a non-trivial linear relation among these three vectors. Okay. Now note that the vector, okay, can be expressed by linear combination. All right. So this vector is in the span of x. All right, and this vector can be written as a linear combination of 1, 0, 0, 1, or it can be written as a linear combination just using a vector 1 minus 1. Okay. So thus, the representation of 2 minus 2 in the span of S as a linear, okay, so as a linear combination of vector in S is not unique. Okay, so you can see that. We can see this vector is in the span of X, but you can have two different representation as linear combination of vectors in the set S. Okay, you can see that. All right, and the next theorem shows that this phenomena occurs if and only if it because that the set X is linearly dependent. Okay. All right, so we will show so suppose S is a linearly independent subset of a vector space. Okay, so S is now each vector U in the span of S has a unique representation as a linear combination of vectors in S. Okay? All right? So now we'll give a proof of that. So assume that U is a vector in the span of S. such that so we assume such that U can be represented in two different ways. Okay, and U it's equal to B1, U1 plus plus B R UR plus BR plus 1 W1 plus plus BM WM minus R. Where U1 up to UR, V1 up to V M minus R, W1 up to W M minus R are distinct vectors in S. Okay, right? So here S is an ordinary set. S is not an index; it's just an ordinary set here. So X is linearly independent, right? And so we suppose that in the span of X there is a vector. This vector can be represented as a linear combination of vectors in X in two different ways here. In this representation, you may select the same vectors, U1 up to UR, to form linear combination, right? So in this, the first linear combination, they are m vectors. For the second linear combination, you have m vectors. But these two use the common vectors U1 up to UR. This is the generic case. So you have U1 up to UR, and the others, AR plus 1 up to AN O. So I think I have some, oh, I see. I'm sorry. Yeah, B1 up to VN W1. Okay. So we have these distinct vectors in X. And of course, the A1 up to AN, B1 up to BM, they are scalars. Okay? So then we take their difference. So 0 is equal to U minus U. Okay? So we take the difference. And we find that this is A1 minus B1 of U1 plus plus AR minus BR UR. Okay? And plus AR plus 1 V1 plus A N V minus R. And the minus BR plus 1 W1 minus minus BM WM minus R. Okay, so this is 0. Okay. Now, so this is a linear relation, okay? So which is a linear relation on the set S, okay? So we have a linear relation. But the set S is linearly independent. So this linear relation and must be trivial. Because if the linear relation is non-trivial, then then the S becomes too linearly dependent from the definition. Okay. But we assume that the premise of the theorem is that X is linearly independent, so that this linear relation must be trivial. So we have that's A1 minus B1 is equal to equal to AR minus BR equal to 0. Right, and BR plus 1 equal to BM or A. The coefficient, all the coefficients should be 0. AN is equal to 0, and BR plus 1 equal to BM equal to 0. Okay, so it turns out that all these are zeros. Okay, they are all zeros, and A1 equal to B1, AR equal to BR. Okay. Okay. So it turns out that this is 0. All coefficients here, they are zeros. And A1 equal to B1, AR equal to BR. Of course, A2 equal to B2. Thus, the two representations okay, given above are the same. Okay, so that they are the same. Okay, and this is the end of the proof. So once the set S is a linearly independent set, then the span in every vector U in the span of X has a unique linear combination, unique representation as a linear combination of vectors in S. Okay, and all right, suppose S is a subset of n vectors, just n vectors. Then every set of more than n vectors in the span of S must be linearly dependent. Okay. Right. So S is a set of n vectors. We don't know this set is linearly dependent or linearly independent, we don't know that. Just a set of n vectors. And then, and if we select more than n vectors from the span of S, right? Select more than n vectors, then for sure this set must be linearly dependent. Okay. So this is a very strong theorem to know. All right, so we let S to be V1, V2 up to Vn. Okay, so it's a set of n vectors, right? And we let m is a number, it's an integer greater than n, and we select m vectors from the span of S. Right? So it's that. And we want to show that U1, U2, and UM form a linearly dependent set. Okay. So you can see it's just arbitrary. It's just a set of n vectors, arbitrary set of n vectors, okay? And then for m greater than n, you just select m vectors from the span of X, m vectors. M is greater than n. Then these m vectors form a linearly dependent set. Yeah. So this is what we want to prove. All right, but because U1, U2, UM, they are in the span of S, right? So we must we find U1 is equal to B11, V1 plus plus B1n, Vn. And finally, UM is BM1, V1 plus plus BMN, Vn. Okay. So because they are in span of X, so they are linear combinations of vectors in S here. Okay, and here, so for some scalars, Bij, I is from 1 to m, and j is 1 to n. Okay, so to show that U1, U2 up to UM form a set which is linearly dependent. Right? So this is our purpose, right? To show that this set is linearly dependent, we must find a non-trivial. So we must find a non-trivial linear relation. Okay, so we want to find a non-trivial relation. A1, U1 plus A2, U2 plus plus AM, UM equal to 0 with the scalars A1 up to AM, not all 0. So we have to find such a non-linear, non-trivial linear relation. This is our purpose, okay? All right, so okay, so we plug. So now, with this formulation, we want to find this, right? So now we have the 0 vector. It's just AI, UI. Okay, so this is the we want to find a non-trivial linear relation such that AI not always 0, right? Okay, but the UI is B, I, J, V, J, J from 1 to n, okay? Because each UI is a linear combination of vectors in S. Okay, so this one, we exchange the order of sum. So J sum over, and the I from 1 to m, and the AI. So so we have B, IJ, and the AI, and the VJ. Okay. Right. So to find this is 0. Okay. So we try. So we will try to find. So we'll try to find the A1 up to AM, not all zeros, such that we try to find A, not all zeros, such that this coefficient of Bj is 0 for all j. Okay, so we try such that the summation I from 1 to m and the Bij Ai is 0 for all j from 1 to n. Okay. All right, and so that we have so because the Bij are known, right? Because they are here linear combinations. Unknown are AIs. So we have a system linear equation to solve. Okay, and this system is homogeneous. Okay, so now we can write it here. It's B11, B21 up to BM1, B12, B22 up to BM2, and the B1n, B2n up to BMN. And here is A1, A2 up to AM equal to 0, 0 up to 0. Now, the matrix, the coefficient matrix has dimension, which is n times m. Okay, so it has n rows but m columns. But you know that m is greater than n, right? By our assumption, m is bigger. So we have more columns than rows. We have more columns than rows, right? So we have more columns than rows. All right, so now since n is less than m, the rank of the coefficient matrix, all right, is no greater than n by theorem 1.3.7. Okay, and the rank is the number of pivot position in the coefficient matrix, right? It's the number of pivot positions, or the number of pivots in the reduced low echelon form of the coefficient matrix. So that they are, okay, so at least m minus n columns, right, without a pivot, right, in the reduced row echelon form. Of the coefficient matrix. Okay, so the corresponding value of unknown variable to this n minus n columns can be selected as free, right? So that they are at least n minus n out of m unknowns A1, A2 up to AM can be selected as free variable. Okay, so the solution is non-trivial. Okay, because we have at least the n minus n unknown AIs can be selected as arbitrary. Free means arbitrary, right? So that's we have a non-trivial solution for A1, A2 up to AM. Okay, so this shows that. Right, so we find not all zero solution, A1, A2, AM, such that this is 0. Okay, so we find a non-trivial linear relation for UIs. So that means that this shows that U1, U2 up to UM is linearly dependent. And we have done. Okay. Any questions? Okay, so you can see from the proof that we used what we learned in the first chapter to solve system linear equation, right? To give us a proof here that to solve our problem, all right? And so that we have such a general theorem, okay? A very nice property to see, to know that, okay? And this is always true for an arbitrary any general vector space. Okay. Okay. Any questions? Okay. So if no questions, I'll stop here. Okay. Mm-hmm.